So what did you say? We got these two blocks, one floats, one sinks. I'm going to make a big version of the one that floats. What's going to happen to it? Raise your hand if you think it's going to float. Anybody want it to sink? Think it's going to sink? Anybody initially thought maybe it would sink? Anybody? No? Y'all were going with floating? Why did you say floating? It's going to float. Why? Go, Sydney, get us started. The density is still the same. Even though it's huge, how does that work? I got this. So if we have a block that's this big, let's say it's, 6 inches big. If it's 3 times that big, that means that each side, instead of being 6 inches, is going to be how big? 18 inches. That's like, what, like this? A block this by this is going to float? Haley, what?
It's also just like the material is the exact same. Like, so, I don't know. I guess it's just more spread out. It's just not, yeah.
Okay, so I'm going to write down what I hear you saying, and then I want to put in some more words. I'm going to let you put the words in, but I want to make sure that I've got it. So you said the material is still the same. And then you said something else, or you started to say something else.
It's more like spread out, because if it's like a smaller block, it's just the bigger block, just material is kind of spread out.
I think I understand what you're saying.
Yeah, like not as compact. Like,
What's that?
Not as like compacted together.
Okay, so let me ask a question to make sure that I'm really understanding. So I've got a block that's 6 by 6 by 6, yes. And I've got a block that's 18 by 18 by 18. In which one is the material more compact?
The one that's small, right? It's the same.
Yeah, it's the same both.
It's the same materials.
No, but this is the important thing. It's really important. It's the same material. It's like you took that 18 by 18 by 18 block and you like cut a corner off of it, right? So it's the same stuff, which means it's the same amount of compactness. Yeah, does that make sense? It's weird to think about, but that's exactly what we're trying to get at. So the material is the same. So I'm going to say, this is very technical terms here. The amount of compactness is the same, right? So the number of atoms or the number of molecules or the number of pieces of matter, whatever you want to call it, per square centimeter or square inch or square whatever is exactly the same. It's the same amount of stuff per piece. We just have more pieces of the same thing. Beth, did you have something else you wanted to add to that, or were you just putting the same kind of words out?
No, that's it.
Okay, are you sure?
Yeah.
Okay. Anything else that you want to add to this? Okay. We're going to jump in and we're going to actually keep doing some of this. I would like for you to send somebody from your table up to get blue paper for everybody. I'll put it right here. We'll mix it up a little bit. There you go.
Oh, I got 4. Yeah. 4
Jeez, Jack. I'll take it back. Thanks.
Let's come right there. Oh, where did you get that pencil?
So, this page is intended to be kind of some guided notes, so it gives you like spots to write your notes in. Okay? There isn't, like if you just took this home and thought you were going to study from it like this, it's not going to get you anywhere, right? It doesn't really have any real earth science information, just some verbs and some nouns and things. So we're going to fill it in, but it's just intended to help you kind of structure what we're doing. So we're going to start in that try it section. And in the try it section, we're literally going to try what we just talked about. So I don't have blocks from bath time blocks. I didn't think to bring any of those from our house, but I do have these little blocks, okay? These little white blocks. They're pretty exciting. You want to feel them? Yeah, you can totally feel them. So anyway, I've got 2 blocks made of the same material. The first thing in that predict section, what I would like for you to do is to compare. There's one that's larger. Which one's bigger? That one, right? It feels bigger, right? I want you to predict which one is going to have a bigger density. So the bigger one is number 4, and the littler one is number 3. So they're made of the same material. The big one is number 4, and the little one is number 3. Which one will have a bigger density? I want you to write down that answer in the predict section. We are not going to, I'm just going to wait for Miss Carmeling to tell me the right answer. That's not what today's about. Okay? I want you to write down your prediction right now. Number 4 is the bigger one, and number 3 is the smaller one. Like, physically, they're larger. Yeah. Jack's apparently taking over this game. All right, so I want to know which one has a bigger density or a higher density. Once you've made that commitment, I want you to take a look at the verb that's right below predict. What does it say? Calculate. So what do you think we're going to do? Calculate. Oh my gosh, we're totally going to calculate it. In order to calculate density, what do I need to do? Mass divided by volume. So fancy this. I measured the mass of these blocks already, and I didn't actually measure the volume. What do you think I may have measured that will help us to find the volume? The length, the width, and the height, right? So I did measure that earlier today, this morning when I got in, so that I could give you that information. And just to expedite this process, we are going to divide our tables so that we can kind of divide and conquer and get this to happen a little faster. So you will need a calculator out. I'm going to let you go do that right now. Go get a calculator if you need one. There are some up there. While you're at it, put your phones away. I don't want to see your phones, and your phone is not a calculator for this activity. You need to have a calculator out. What's up? If you would like to share with your partner, that's okay with me. Yeah, that's fine. We're only going to do this one calculation today, so I just want to make sure that everybody has had the experience because, you may need to do this calculation, I don't know, on Wednesday when you can't share with anybody else. You know what I'm saying? Yeah. You get what I'm saying, right? Hint, hint. All right. All right. All right. So, my friends, we are going to divide up this table, 1, 2, 3, 4. You guys right here are going to be in charge of block 4. And you 3 tables, you're going to be in charge of block, anybody want to guess? 3. What? All right, so let me tell you some information. Oh, hold on though. Let's make sure we know this because, friends, I need to make sure that you understand this. Everybody needs to understand this. We spent some time with this on Friday. So everybody's been exposed to it, but if you don't know it yet, this is your opportunity to understand how to calculate density. Are you with me? So take advantage of it. Take advantage of it. How do we find the volume? We kind of said it, but I want to write it down officially here. Length times width times height. Yeah. It doesn't work unless I do that. It's really annoying. But eventually it will break, but until then it's already broken. So, it's like, how broken do you want it? All right, so block number, I told you guys were 4, is that right, over here? Block number 4, the mass, you guys are block 3. The 3 tables are block 3 and the 4 tables are block 4. That worked out well. The mass is 58.9 grams. The length is 7.3 centimeters. The width is 7.7 centimeters. And the height is 1.8 centimeters. If you are in charge of block 3, the mass is much smaller, 38.9 grams. The length is 8.8 centimeters. The width is 4.2 centimeters. And the height is 1.8 centimeters. They're the same height. Huh. There you go. All right. So now, again, I want to remind you that I want everybody to know how to do this. So even if you are sharing a calculator, I would like for you to take advantage of this moment to spend the time to learn how to do this. Okay? Everybody's going to calculate the density of one of the blocks, either block 4 or block 3. When you have your density, is density just a number? No, it's a number with a what after it? Whoa, it's got to have something. It's got to have a unit, right? Yeah, so figure out what that unit is as well. Not just the number, figure out the unit as well. Yeah, what's up? Did you say, can you come in for a second? Yes, what's up? Let's round to the nearest 100. So, 10 to 100. Okay, yeah. Why don't we all round to the nearest 100? That'll just keep things consistent, right? Because they're not perfect numbers. That sound okay? So once you've got it, check with your table. See if they agree. And once they've got it, maybe check with the other tables and see if they agree. All 4 tables should agree here, I hope, since you all have the same numbers. And all 3 tables here should agree. So double check. Check with your teammates.
I got it.
100th, so that's 2.
So I am so bored.
All right. All right, are we ready? Maybe? All right. Let's see. Gracie Carr, can you tell me what you guys got for, you did block 3, right? What did you get for the density? 0.58, and the units are grams per centimeter cubed. It's a weird unit, right? It's weird, but it's the mass divided by the volume. So the mass is in grams. The volume is in centimeter times centimeter times centimeter, which is centimeters cubed. So grams per centimeter cubed. Thank you so much. All right, Angel. This is the moment of truth. What did you get for the density of block 4? 0.58 what? Awesome. Hot diggity, look at that. It's the same thing. Even though, I'm glad you did. Good for you. I'm hoping that most of you did. Now, if you did not predict that, that's okay because that's what we're here for, is learning, right? But the thing that I want to remind you about, I want you to look at those. So Jack told us that this one was a lot bigger. It looks bigger, right? It looks big. And indeed, it is heavier. It's got a lot more mass than block 3 did, but it's got more mass and more volume. More mass divided by more volume, less mass divided by less volume, they have the same density. Okay? So if your prediction was that they would be the same, you put a little star by it or a little smiley face or whatever makes you happy. If you did not predict that they were the same, then I'd write down, oops, I was misunderstanding. I screwed up a little bit. Oh, well. And then fix it so you know the right answer. Okay? And then we're going to move on. We're going to write down Things to remember, number 1. So you see that little space that says things to remember, number 1? This is it. Boom. Objects that are made from the same material have the same density. That's an important thing to know. Objects that are made from the same material have the same density. So this goes right in your note sheet where it says things to remember, number 1. You're going to write that down. Okay? I'm going to write that down. Things to remember, number 1. Objects that have this are made of the same material have the same density. I have a question for you. If 2 objects have the same density, are they necessarily made of the same material? No, they're not. You can absolutely have 2 things that have the same density that are made of totally different stuff. It's kind of weird. Take chemistry, take physics, we'll talk about it, but I just wanted to point that out. All right, we good? All right, step 2 says test it. Test it, we're gonna make a prediction. So these have the same density. Do you remember what the density of water is?
1.
It's 1. So I would like you to make a prediction. I'm going to put one of these blocks, or maybe both of them, into this water right here. It's just plain old water. I just put it down here so we can take a look at it, and I'll turn the camera on. Make a prediction. What's going to happen when I put these in water? Make a prediction. You can talk to your table mates if you want. That's fine.
Sorry.
The enthusiasm there was great. All right. Did you make a prediction? We'll see if I have this set up well still. Okay, so in theory, can you see this? Hello, there's us. Can you tell what's going on? Yeah? That's just the way that the lens is. I don't know. I'm not going to spend time refixing right now. So I'm going to go ahead, and so can you see like the water line is right here? Yeah, so we can put the block in and find out. Here we go. Oh my gosh! Were you right? You were right. So, raise your hand if you're right. Yeah. Sweet. Why does it float? Less dense than what? What about this one? What's going to happen?
Float.
It's going to float too. Yahoo! That's exciting. All right, good show. Hot diggity, right? It's like my thing. I like it. It makes me happy. It makes me happy. All right. Let's write it down. Okay, so your prediction. Oops, that didn't go yet. Yep, we're going to write down that they both floated, and then we're going to write down for sure why, right? We know that the blocks floated, and we know that they floated, just like Hannah said, because their density was less than the density of water. Density of the block, because it was 0. Was it 5.8? Is that what you guys calculated? Grams per centimeter cubed is less than 1 gram per centimeter cubed, which is the density of water. We good? All right, I'll be right back. All right, it's cold. Woo! What is this? Ice. What's going to happen when I put it in there? What? What happens? It will melt eventually, right, if I leave it there? But take a look at the ice. Can you see it right here?
Is it right after water?
It's right at the water, but is it sinking down to the bottom? No. It's not sinking down to the bottom. If it's not sinking down to the bottom, what do you know about the density of it?
It's more than.
It's less than water.
One of the two.
It's the same. It's water. It's the same. Exactly.
Okay, that's why I do this, right?
But it's
So think about if you ever put ice cubes into your water, or into your soda, or into your whatever, right? Do they sink? So if you no. Oh, does it?
I feel so.
Okay, better. It better, right? It better because if it doesn't, But if you fill the whole thing,
No, it doesn't. What do you know?
I mean, unless you have a lot where you just hold it down.
Next time, unless your cup is full.
we're gonna do this.
Next time they explore what I can do anything.
I don't know, not water.
Yeah, but I put like a lot of
Stop it.
Was your drinks always like everyone? Like, yeah.
No, because
Like,
like,
All right, ladies and gentlemen, we're gonna look at this from a scientific perspective. I need your attention, my friends.
either way.
So right now I've got a cup. It's got ice in it. Is the ice sinking or floating right now?
It's not new because no water.
What does that mean, right? What does it mean, right? There's no water, so like
Sinking in the air.
it's sinking in the what?
Air.
It's sinking in the air. So, what do you know? What do you know about the density of ice as compared to the density of air?
It's a lot more dense.
It's more dense. It's more dense, and we know that because it's sinking in the air. Everybody good with that? Okay, so density of air is less than the density of water. Now, Beth is going to go fill us up at the sink over there for me. Go ahead and fill it up. Maybe not all the way to the top, but close.
Watch your flow.
Life experience is important, my friends. Science is life. Like we see it all the time. So what happened?
It's staying there.
It's floating in the air? Wait, what? You got like a different reality space. I don't know.
It's staying like right there. Really move.
It totally moved, friends. I want you to stick your finger there and stick your finger underneath the ice and see if you can feel water underneath the ice.
Oh, yeah. It's,
Oh,
I don't think
it did float, didn't it? That's okay. You know what? We're not judging, we're only learning, right? That's what we're here for. We are learning about science. So, let's put this together. So we can see that the ice does float. We can see that the ice does float. We either see that every day when we're, making our ice water at home, or in our science lab, or in our special cup. Either way, we can gather. So this is our follow-up. The follow-up question is, what happens to ice? We're making an observation here. We're not a prediction, but it's an observation. The observation is that ice floats, right? Ice floats. Maybe we should be specific. Because does ice float in air? No. So as scientists, we need to be a little more specific, right? Ice floats in water. Indeed. Now, we said this before, but we haven't written it down yet. What does that mean about the ice? The density of the ice as compared to the density of water?
No, it's less dense.
It's less dense, yes. So the density of ice is less than the density of water. Let me ask before I move on. Are you guys okay with this? Have we seen this before in math? Is there anyone who's like, this little guy here means less than, yeah? Yeah, just in case, because I don't want anybody to turn their brains off because they don't love math. So this means less than, okay? Oops, that's a really funny smiley face. He's like, woo! Let me try that one more time. It's like a Monday morning smile. There we go. All right. So that little sign means less than. So the density of ice is less than the density of water. So now I'm going to ask the question that Hannah asked earlier because she wanted it to be the same. Hannah, why did you want them to be the same?
Because it's water.
Because it's water. And we said, this is a big deal, you guys. This is science that's happening in front of your eyes here. We said in things to remember, number one, friends, I don't know why you're talking. If you have a question, I'd be happy to answer it. Or if you have a question for somebody else, I'm happy to answer that. But otherwise, we need to stay as a group here, please, okay? We said in number one that objects made from the same material have the same density. And then Hannah says, but ice is water, which is true. But there's some weird stuff happening here. What? What's up?
Isn't like water a liquid? Isn't ice kind of more of a solid?
Right.
So it wouldn't be
That's
the same
weird.
material.
It's weird, right? Because ice is like the solid version and water is like the liquid version, but they're both made of, do you guys know what ice and water are both made of?
H2O.
H2O. So this is a little chemistry for you. H is what? Hydrogen. And O is oxygen. And do you know what a water molecule looks like? Does anybody know? Are you okay? What are you doing, friends?
Okay.
Okay. Do you guys know what a water molecule looks like?
Yeah.
Looks like Mickey Mouse. It looks like Mickey Mouse. Okay? Shh, friends. Like, are you okay or no? Do you need to go do something? Okay. Let's just make this a productive day. So there's your oxygen, and then you've got your hydrogens that come off like this. Okay? Okay?
Is this like the bottom of it?
Yep. And you can put them right next to it, but it doesn't matter. There's a little bond there. The reason I want to show you this is because the next picture I'm going to show you has a bunch of these in it, and I want to make sure that you understand that. Okay? So water is made of oxygen and hydrogen. Ice is made of oxygen and hydrogen. Same molecule. But here's the funny thing. The density is different. The density is different. Let me show you a picture. Here's a picture of ice. Here's a picture of water. Why don't you go take a walk for a second? All right. Go take a walk. Come back when you're feeling better. Ice. Water. What do you notice about these two pictures? Just go. Don't be a thing. Go. What's different, guys? Come on. What do you see? It is for sure more organized. I absolutely agree. It's more organized because it's crystallized, right? Yeah. And what else do you notice maybe about how squished together or spread apart these little molecules are?
Water has more. It's very squishy.
They're much more squished together, aren't they? And what did we talk about at the beginning of the day? Haley was talking about this. Which one of these is more dense?
Water.
The water, right? The water is more dense than the ice. It's got more molecules in the same volume. So in that little section of your paper, it said, discuss and draw. I'm going to show the picture again. You do not need to draw those little green things. Those are just, don't worry about that. But I want you to draw some ice molecules in a circle. I want you to draw some water molecules in a circle. And the thing that's super important is that the number of molecules, or the amount of matter, I'll say, we'll keep it simple here. The amount of matter in the circle for ice is less than for water. This means that ice is less dense than water. How are we doing?
So basically when we're drawing this, we just have to make sure that the ice one
Has fewer of the little molecules, fewer of the pieces of matter than the water does in the same size circle, right? Same size circle means like the same volume, and there's less matter in that volume. We doing all right? So I've got another picture to show you as soon as you guys are ready. We ready?
I needed that.
Another moment? Okay. So if you remember, things to remember, number one said that objects made from the same material have the same density. And then we said, well, ice and water are a little different, right? One's a solid, one's a liquid. Now I'm going to throw a little bit of a wrench into this. because I'm going to show you two pictures of water. Okay? Two pictures of water. So this is the extension part. We'll look at the pictures and then we'll answer the question. There's warm water and cold water. Yeah.
Okay, so in warm water, the molecules or whatever are moving faster. So there's not as much in the space. But in cold water, they're more packed together because they're moving slower.
Absolutely. Let's write down exactly what he said. So warm water, the molecules. So this is going to go in the compare. So the question is, which has a higher density? Okay. In the compare section, so again, this is in the compare, the extension compare. Which has a higher density, warm or cold? Jacob said that the molecules, or I'm just going to say the matter, is moving. What did you say?
Faster.
It's moving faster in the warm water. And then what was the next part of what you said?
So they're, or look about the cold water.
Either one. Go ahead. Just keep talking.
So the cold water, it's not moving as fast, so they're more like together. Yes.
So not moving as fast, which means that the molecules or the matter, and you don't have to write molecules or matter, just pick the one that you prefer. Pick the one that makes the most sense to you and your brain, okay? The matter is more compact or is more tightly packed, I guess. Okay. So it's all about how fast the molecules are moving. The warmer something is, the faster they move, the less stuff there's going to be in any space. Okay. So now, my next question, are we okay with this? Yeah? My next question for you is, oops, wait, come back to there. I would like for you, so that was your compare. My question now is, in the reflection section, that rhymed. In the reflection section, which one's going to float? What? Warm water or cold water? Which one's going to float? What does that mean? Which one's going to go to the top? Which one's going to go to the bottom? That's my question for you. Which one's going to float?
Cold, like, sink,
and then maybe answer that question too. So write it down and tell me why. Why do you think one of those is true? What's that? You don't know? Okay. Gracie's like, what? What is this talking about? All right. What's up? You got an answer? What is your answer, Colin?
So in cold water,
Friends, yeah. It's more dense?
And then the warm water, since it's more fast and like spread out, it's not as dense. So it would float.
Okay. So you think that, so long story short, you think which one's going to float?
The warm water and the cold water sink.
Warm will float and the cold will sink. So now we're going to find out if he's right. So I got a little video for you. I tried to do this demo. Last year I tried to like make it happen, and you know those YouTube people are so much better at doing those things. Like they probably video it like 27 times as opposed to me just doing it one time. So here we go. I'm going to turn, hold on, I have to turn the volume on so that it actually, you can hear it as well, because this isn't going to go. Hold on, pause. Okay, this is a really fast video, so you got to watch fast. He's got safety glasses. Yeah. Here we go.
Water, so water can't damage.
All right, here we go. Oh, there's no music. You just have to watch. Oh, let's get rid of this ad.
Adult supervision.
Okay, watch. Shh.
looks like beer.
Okay, so before we move on, I just want to make sure you're understanding. So the blue one is what kind of water? Cold water, and the yellow one is hot water. So he's got a cold water and a hot water. We put a playing card in between them, or on top of the yellow one. He's going to flip it, and he's going to pull that card out. He's going to do the same thing, but what's the difference on this one?
He has cold on the top.
He has cold on the top and warm on the bottom, right? So what was your prediction? What did you say, Colin? You thought what was going to happen? Warm is going to float. So now we're going to find out what's going to happen. Because they're going to pull the card out.
She wants to scream. So you got blue and yellow mixed green.
I know, right? It's exciting. So that was really fast. Did you catch that, though?
Yeah, the blue,
I'm going to go back to the picture. So what do we see here?
they were mixing, so they were like changing spots.
They were mixing because they were changing spots because the warm water wanted to float and the cold water wanted to sink, right? Whereas this one over here, I think this is so cool because even though there's nothing dividing these two, the hot water stays up here and the cold water stays down here because it's floating. Like literally that's what's happening. The hot water is floating on top of the cold water. You with me there? Kind of cool. I've tried it before. It's just like to get it all lined up. It's just tricksy, you know. I mean, it works. It just makes a bit of a mess. So this is more succinct. Takes 1 minute as opposed to 20 minutes for me to get it all set up. Yeah. All right. Let's go back. And now I want you to make sure that if you don't have that written down, that you write it down right now. So the warm water is going to float. The cold water is going to sink. You could draw a picture with those bottles if you want to remind yourself of what you saw. Okay? Remind yourself of what you saw. And we are ready for thing to remember at number 2. Here it comes. Things to remember number 2. Objects made from the same material can have different densities if their temperatures are different. Okay? If the temperatures are different, objects made from the same material can have different densities. Generally, the warmer the material, the less dense it is. So it's kind of funny because this whole unit, have we been talking about density? Has this whole beginning of the second trimester been about density? No. In fact, I only threw density at you on Thursday at the end of the day, and then we did it all day Friday. We've been talking about all day today. Now is when we're going to put it all together. So we're going to put it all together a little bit now and put a little bit together tomorrow at the beginning of class. But I want to think back to the very first thing that we did this unit. If you need a reminder, you're going to look at that window. You're going to look over there at what we drew. Do you remember doing that at the very beginning of this unit? The very beginning of the trimester? In the application section, we're going to start by recalling the slice of earth. So here we go. We're going to draw our picture. Here it is. The slice of earth. We did this at the this was like our notes part. There were 4. Yeah, just make like a piece of pie. Okay. There are 4 layers. I guess it should go down to a point, shouldn't it? There are 4 layers of the earth. Do you remember what they are? Crust, mantle, core, and core. That's true. That's true. Let's draw them. So you got the crust, and it's pretty thin. And then you've got the mantle, and the mantle's pretty big. And then you've got the inner core, and you've got the outer core. And these are not drawn to scale. Oops, I just did that. I just labeled that the inner core. Silly me. Come on, Carveling. Outer core. And then we've got the inner core. Okay. And for today and a little bit tomorrow, we're going to focus on the mantle. So my question for you is, within the mantle, well, first of all, what is the mantle made of? Molten rock, also known as magma. It's not lava until it gets out the crust, right? So this is all magma. It's all liquid. Where is the magma the warmest within the mantle? I'm going to go with top or bottom. You think it's really hot up here and cool down here?
No.
The further you get towards the middle, the hotter it gets, right? The hotter it gets. So the mantle is hottest, hot down here, and it's cooler up here. Okay? Now, let's think about what we just saw. If you have hot magma down here, what do you think the density of that hot magma is going to be relative to the cooler magma up here? It's going to be less dense. So what do you think is going to happen with that magma that's down at the bottom and really hot? What's it going to do? It's going to go up. And if it goes up, then something else has got to take its place. What do you think is going to take its place? The cooler magma. Are you with me there? Yeah. So this density stuff actually matters, friends. This is why we're doing it. Okay, so we're going to write this down, that the hot magma at the bottom of the mantle is less dense than the magma near the crust. Okay? And as a result, you're going to get some rising and some sinking. I'm going to show you a video here. We've got 4 minutes or 3 minutes, and we've got a 3-minute video. So I'm going to show you the video, and then we'll talk about it tomorrow. I just want to show you where it is or what it looks like. So take a look here. So pay attention. Don't put your stuff away yet. Don't put your stuff away yet. Don't do it. Don't do it. Oh, there's an ad. Silly ad. I know, right? That's a fun thing. Take chemistry. You'll do it. It'll be fun. All right, here we go. Skip ad. Oops, I need to make sure that my sound is on, though. Hold on.
Not a things
Oh, here we go.
you'll ever see in a science class.
Okay, take a look.
Have you heard that heat rises? Well, here you can see it's true for yourself. I've got some food coloring on the bottom of a plastic container,
Watch, watch,
and there's a
watch.
hot mug right underneath the red food coloring. As it's heated, the water rises. But I want you to look closely and notice something else. The blue on the sides is being drawn in. You can see it better when I speed it up. Here's the thing I want you to remember. When water moves from one place, it doesn't leave a void behind. Water from somewhere else has to move in to take its place. That's why you can see the blue food coloring coming in from the sides. You can see it better from above. Watch that blue food coloring get drawn in. Do you see it? The hot water reaches the top, and then it gets pushed toward the edges by more hot water rising from underneath it. As it goes out to the edges, it starts to get cool, and cool water sinks just as hot water rises. And if you watch really carefully, you can see it sink and get drawn back toward the middle. These are
Your
called
test is on
convection
Wednesday.
currents, and you can
No,
see
this
them
is not
here in
required, but enjoy.
oceans. They're one of the major things that drive ocean currents, especially in the deep oceans. But it's not hot water rising that drives the ocean currents. It's really cold water sinking up near the poles.
Have a great day, bye.
Here's a
See you
piece of ice
tomorrow.
that I froze with some blue food coloring in it. So you can see how cold water